Welcome. Today we're going to talk about developing transferable freeze-drying protocols using Accuflux heat flow control and a micro freeze dryer. My name is Thompson from Millrock Technology, and I'd like to thank Chiming Wang and Cindy Ryder for their help in developing a lot of the content of this production. A little discussion on scale up and transfer. The main goal is to maintain an equivalent product temperature or thermal history between the lab and commercial processes. So the instrumentation that we use for developing protocols needs to give us the critical process parameters to ensure that we understand the thermal history in both the source or lab system and the target or commercial process. So freeze dryers, we're going to use the vial heat transfer coefficient, otherwise known as Kv. There are two methods that we're going to discuss on how to determine Kv. The first is Kv Gravimetric, which is a method that uses the weight loss per time during a short primary drying cycle to determine Kv. The second is Kv Accuflux, the use of a heat flow measurement device between the vial and the shelf. So the objective for this presentation is going to be threefold. First is to compare the Kv Accuflux versus Kv Gravimetric in a Revo-sized lab scale freeze dryer, which is a 6 square foot freeze dryer. Gravimetric is basically a heat map that we're going to create with 336 vials, and the heat flux sensor looks like this here. Then we're going to compare Kv Accuflux versus Gravimetric using 19 vials in a micro freeze dryer. We're going to have a little stack of 19 vials that fit into this, and we'll be able to take a look at the Kv across that batch. Once we do that, we're going to develop a protocol in the micro freeze dryer and transfer that to the Revo and take a look at the thermal history. So let's start off with Kv Gravimetric. To measure Kv gravimetrically, we're going to add water, in this case 5 mils of water to a 10 mil vial, put an igloo stopper on it. There's going to be 336 vials on a single shelf. We're going to run our shelf at minus 20 degrees with a chamber pressure of 100 millitorr. We'll weigh each vial and mark its location on the shelf. Then we'll freeze the product at half a degree C per minute to minus 40, and we'll start our primary drying cycle. We'll stop the primary drying cycle when during a point at which we have a steady state, but it's far enough into the run that we have significant data to make our measurement. In this case, around 300 minutes into the run. We'll again weigh each vial, calculate the mass loss per time, and use that information to determine Kv. There'll be 336 calculations. For each vial, we'll use a batch average product temperature, and we're going to use the shelf temperature for the calculation. It's important that during these measurements, we understand where the measurements are and we're consistent. We're going to use the shelf surface temperature, not the inlet temperature. The shelf surface temperature provides the true Kv and has the least variation. A large freeze dryer is going to have a larger temperature difference between the inlet and the shelf surface than a small freeze dryer, so the only way to really do this is to measure the shelf temperature at the surface. We're going to use the batch average, which is the easiest way to do it for gravimetric testing. And we're going to use the time from steady state until we stop the process. We're going to quickly ramp the set point up to temperature, wait for steady state, and then use that period of time as our time period. We always use a partially stoppered vial for the experiments because it's the most realistic methodology. Here's a heat map that is created for the 336 vials. You can see we calculated a batch average of 21.46. The edge vials on the outside have a higher Kv than the center vials, and T marks where we had our thermocouples for our measurement. When we measure Kv, we do that in watts per square meter degrees C. If we do an analysis of the Kv for the 336 vials, We can look at the entire batch, or the 12 by 28, 12 rows by 28 columns, and we get a gravimetric kV of 21.46 for the entire batch. But let's break it down a little bit more. If we look at the 8 by 24 rows, we get a kV of 19.18. If we look at the 4 by 20, it's 18.92. And if we just look at the 6 center vials, it's 18.90. We can see that if we eliminate the edge vials, the outer 2 rows, that we get a fairly similar kV here. In fact, it's almost immaterial as far as the measurement goes, as the difference there. So once we eliminate those edge vials, the center vials are pretty consistent in kV. Kv Gravimetric has some major advantages. The advantage is that data can be collected and you can look at the desired results, a batch average or just the center vials or just the edge vials. The disadvantage is it's extremely labor intensive. It's subject to error due to large number of manual measurements. And you've got to use a batch temperature average, not the vial, not the actual vial temperature. The calculation is subjective to the time that's used, and it's a challenge to get Kv gravimetrically for production units, so it may not be realistic for you to use. Now let's take a look at Kv determination using Accuflux. This is a heat flux sensor on a shelf. It's a 2.5 inch by 2.5 inch surface. It's installed directly on the shelf and placed between the vial and the shelf surface. It does measure the shelf surface temperature, which gives us a very accurate kV reading. Its output is in watts per square meter, which it gives us an extremely easy way to transfer or calculate kV. In our case, we actually had a 12 by 24 shelf with 2 sensors mounted on the shelf, one in the center, one at the edge, in these following locations. To determine kV, it's pretty straightforward. We're measuring the heat flow through the heat flow sensor. We're measuring the shelf temperature on the heat flow sensor. And we have thermocouples in the vials, so we're measuring the product temperature. So just putting those together, we get kV for what we call Kv Accuflux for the shelf. That's the heat flow coming in from the shelf surface. There is another component of heat transfer, or other components of heat transfer, including gas conduction and radiation, that we can call Kv other, that we're not measuring with the heat flow sensor. So how do we determine Kv for the entire vial if we're not measuring Kv other? We do it this way. We perform a full primary drying cycle, and we measure Kv Accuflux at steady state. So at a point in time where we've reached the steady state, where the shelf has gotten up to temperature, the product has stabilized, and we're actually measuring the kV from the shelf using the heat flow sensor at steady state. We determine the amount of heat flow from the shelf during the entire run. So we measure the amount of heat flow coming from the shelf, and we compare that to the total heat of sublimation, which is a calculation. We determine that by taking the mass of the product that's in there and the heat of sublimation. Since only a portion comes through the shelf, we divide the amount that we've measured by the theoretical amount, and we get the percent that came from the shelf. So by doing that, we get Kv Accuflux total, which is equivalent to Kv gravimetric. Here's an example. When we're running a run, we measure Kv Accuflux of the shelf at 15.1 at steady state. During the entire run, we accumulate 4.2 million joules of heat, but actually the theoretical was 4.7 million joules of heat that should have been removed. So only 90% of the heat was accumulated or measured during the run. That means 10% came from someplace else. So to figure out what Kv total is, we simply divide Kv Accuflux from the shelf by the amount of heat that came from the shelf, and we get our final number. In this case, 16.78 watts per square meter degree C. So let's compare the heat flow measurement versus the gravimetric. we look at the 4x20 Kv Gravimetric here of 18.92, and we compare that to our Kv Accuflux that we measured in the real situ here, and we have 18.01. If we just look at the 6 center vials where the actual sensor was, it's 18.90 versus 18.01. Extremely good correlation here between the two readings. If we look at the edge vials, this is where we had our our edge sensor. The outer 2 rings of vials resulted in a Kv gravimetric of 24.5. The Accuflux reading was 23.7. If we use the outer 3 rings, we get 23.08 gravimetrically and 23.71 by measuring with the edge sensor. If we just look at the vials that were underneath the sensor, gravimetrically we measured 23.48 kV versus 23.71. Again, a very good correlation in measuring edge vials as well. So if we compare the two measurements, we can take the average of the center sensor plus the edge sensor, divide that by 2, essentially add them up and divide them by 2, which gets the average. And that gives us a Kv Accuflux reading of 20.86. We compare that to the gravimetric reading of 21.46. Extremely good correlation between Accuflux and gravimetric in the Revo series. Very high confidence level that we can use Accuflux to replace Kv gravimetric, which will save us a lot of time and effort in the future. So now let's take a look at Kv Accuflux versus Kv gravimetric and the correlation in a microfreeze dryer. First, let's the microfreeze dryer is, or explain what a microfreeze dryer is. It's a freeze dryer that processes a small batch of 19 vials or less, and it has all the latest technologies. We're not going to use all of these technologies, but it's important for us to understand the capabilities. We could actually use controlled nucleation. We have the Accuflux measurement in there, which gives us all our critical process parameters, including Kv. It has a special technology called LyoSim, which allows us to simulate center and edge vials. And it also has our LyoPack control system, which determines and displays all the critical process parameters. So it can determine Kv, mass flow, cake resistance, and all the other critical process parameters. And it has the ability to test the effects of different freezing methods and drying conditions. Here we see 2 microfreeze dryers in a lab. What critical process parameters can be determined by the MicroFD using Accuflux and LyoPack software? Obviously, we can do the shelf temperature. We can either use the shelf inlet temperature or the shelf surface temperature. We can determine the product temperature using a thermocouple, or conversely, we can plug Kv in and not use a thermocouple and determine what the product temperature is. It has both a Pirani and a capacitance manometer built into the system, so we can do the vacuum level and do a comparative for the end of primary drying. We'll have a direct output of the vial thermal conductivity, called Kv. Will give us a direct measurement of mass flow per vial and for the entire batch. And it'll also show us cake resistance of the product. Some of the control processes that are unique to the system are, we can either use a recipe program for freezing, we can add controlled nucleation, we can do a post-nucleation heat flow control, which is extremely unique, which gives us a uniform crystal growth inside the vial. So controlled nucleation gives us a consistent batch starting point, but since only about 10% of the product is actually nucleated, 90% of the freezing takes place after nucleation. And you need to, if you use heat flow control, you can improve the crystal structure in the vial. We can determine the end of freezing, and there's studies going on right now where we're looking at determining secondary crystallization of things like mannitol. In primary drying, we can use a recipe program. We can control the shelf temperature based on the product temperature and optimize the cycle. and we can determine end of primary drying using the porosity versus the capacitance manometer. Here's a quick example of the cake resistance versus time and the mass flow versus time for center and edge vials. And this just shows the capability of the system to give us the critical process parameters that we're looking for. What is LyoSim? LyoSim is a patent-pending technology that is a temperature-controlled ring that's closely coupled to the vial stack. We did testing with the product, cooling the product chamber wall, and didn't come up with satisfactory results. It didn't give us the uniformity across the batch that we expected. And so we tightened up the control using what we now call the LyoSim ring. That LyoSim ring is independent control from the shelf. It tracks and follows product temperature in a way that you define. And we use conduction blocks that give us good contact or close proximity to any size vials. Because of the unique design, it can model center or edge vials. Let's take a look at what that looks like. How is LyoSim used? For example, for center vials, we can set the temperature of this ring to a couple degrees below the product temperature and track the product temperature, and it'll simulate vials outside of the vial stack, essentially making it think that it's center vials. We can also do an edge vial effect where we set the temperature of this ring slightly above the product temperature, and it makes it believe that it's an edge vial. Very unique technology, extremely important for using a small batch of product. It gives you the best results of anything out there. Let's take a look at what that means. If we look at gravimetric results using LyoSim in a microfreeze dryer, here's a heat map of Kv across the batch at minus 20 degrees. We have a batch average of the Kv being 22.08. Inner 7 vials are 22.53. The outer 12 vials are 21.82. Very close standard deviation and correlation. All 19 vials in this case behave like center vials. If we compare the Kv gravimetric results to Kv Accuflux, we get Kv gravimetric readings of 22.08. We use Accuflux, we got 22.16. Extremely good correlation between Kv gravimetric and Kv Accuflux, which means Kv Accuflux can be used in place of the labor-intensive gravimetric readings or gravimetric process. So we've shown things. First is develop a protocol that is very similar to the center vials on a larger freeze dryer, and second, can be used to determine Kv for that product, which can be used for transfer. Let's take a look at how we would transfer using Kv. In this simple slide here, if we know the Kv in a source system and the Kv in a target system, and we know the shelf temperature, we can calculate the adjustment in shelf temperature to produce the same results. In this case, the shelf surface temperature was minus 1.5 based on the difference in Kv. The shelf surface target temperature would be minus 0.3. Now, knowing that the target system has an offset difference between the inlet and the shelf surface, we've got to adjust for that. So we do make that adjustment, and we have a shelf target temperature of about 1 degree C. Just based on using the batch average Kv. If we're using the center vial Kv, because essentially the microfreeze dryer is simulating center vials, there's a slightly larger difference in Kv, 22.16 versus 18.01. In this case, we'd need to run a shelf temperature in the target system of about 4 degrees versus 0 degrees in the source system. So just to be clear, we ran a 0 degree protocol shelf temperature in the microfreeze dryer, which resulted in a slightly lower shelf surface temperature. And we used that for calculating the target shelf temperature. and we had to take into account the offset difference between the shelf inlet and the actual shelf surface. Let's take a look at what that looks like. We're going to use 5% mannitol, and what we're going to do is we're going to run 19 vials with 2 ml fill in a 10 ml vial using 5% mannitol in the MicroFreeze dryer. We'll use 336 vials in a Revo. And the first thing we're going to do is we'll run the MicroFreeze dryer at 0 degrees, where we have a Kv of 22.16, and we'll get a thermal profile. Then we're going to do the same exact run in the Revo just to show the difference. And then we'll put in the offset calculated based on the Kv of the center vials. In this case, it'll be a +4 degree shelf temperature in the Revo. Here's our freezing comparison between the two systems. These are the temperature profiles. The MicroFreeze dryer, the product temperature is reduced, or the shelf temperature is reduced at ½ degree C per minute to -40, and then an annealing step is added at -15. You can see the product temperature comes down, nucleation occurs, and the temperature profile follows. In the MicroFreeze dryer, the nucleation temperatures were somewhere between probably -8 and -10 degrees centigrade. In the Revo, about -9 to -10 degrees centigrade. Very good correlation from a nucleation temperature and from a temperature profile. Let's take a look at the heat flow. If we take a look at the heat flow profile between the two, it's very telling. We can see that the heat flow profile in the MicroFreeze dryer drops down as the product is crystallizing and freezing, and comes back up till it's stable. And then we add the annealing step here, where the heat flow goes up, comes back down and stabilizes, and we've reached the end of our annealing process. If we take a look at the profile in the Revo, we have the center vials in red, the edge vials in blue. We get an almost identical V pattern here in the freezing process. And what's important to look at here is the magnitude of the heat flow during the cooling process. We're around -1600 watts per square meter in the MicroFD, about -1600 watts per square meter. And the time is pretty similar here, which means that we've got very similar crystal structures being formed. We look at the annealing step. Again, very similar heat flow patterns between the two systems. This gives us a very high confidence that we've frozen the two systems very similarly. We then take a look at the two systems overlapped with the heat flow and the temperature profile. Again, very similar thermal histories between the two systems. Now, one thing to point out is that during the annealing step, we see a droop here in both systems, both the MicroFD and the Revo, that we can basically say that a secondary crystallization event took place. We're doing more studies on that right now. We'll have more available in the near future. Now let's take a look at the primary drying portion of the thermal history. And we're going to compare the MicroFreeze dryer product temperature average and heat flow versus the Revo at 0 degrees C. In the Revo, we have two lines here. If we look at the heat flow for center vials and the heat flow for edge vials, we can see it straddles the heat flow for the MicroFreeze dryer. And temperature-wise, we have the temperature of the MicroFreeze dryer, which is simulating center vials, versus the center vial in the Revo at the same shelf temperature. If we just transferred the protocol from the MicroFreeze dryer to the Revo, we would have a very conservative run that would move and transfer the protocol very conservatively and be a very robust cycle. But we want to be a little bit more aggressive. If you remember, we calculated a 4-degree difference between the shelf temperature in the MicroFreeze dryer versus the Revo. So we're going to use the MicroFreeze dryer at 0 degrees and compare it to the Revo with a shelf temperature of +4. The important point to look at here is the heat flow of the center vials versus the heat flow for the MicroFreeze dryer are almost identical. In fact, extremely well correlation here, extremely good correlation. We look at the product temperatures. There is a slight difference here. The micro-freeze dryer ran a little bit lower than the center vials in the Revo. We can say that this +4 was probably a little too aggressive, and a little further experimentation would probably show that a shelf temperature of +3 in the Revo would have been a perfect solution to give us an identical thermal history between the two systems. This is a pretty amazing conclusion, using 19 vials versus 336 vials and getting almost identical thermal histories here, showing a very promising concept. So we have a couple conclusions we can make. First is the Kv Accuflux can replace Kv Gravimetric. Accuflux eliminates the need to weigh the vials and saves you a lot of time and aggravation. And that the micro-freeze dryer can be used to develop protocols, and the cycle can be transferred to a larger unit using Kv. Today we looked at the transfer between a micro-freeze dryer and a Revo. We could also look at the Revo to a production system. Now, if the Revo to production system works, then why couldn't we just eliminate the middle step and go right from the micro-freeze dryer over to the production system? Experiments are in progress right now to determine the feasibility of this. Thank you for your time and your attention. If you have any questions, feel free to contact me at my email address, tn@millrocktech.com, or at 845-339-5700. You can ask for sales, and they'll be able to help you out. Thanks again. Look forward to hearing from you.